My dear students, good morning. I'm going to discuss with you now material of the term 3 that started with the elements in the periodic table. We are going to explain the periodic table, how it's divided into different groups, and predict the physical and chemical properties of each group. Let's get started. The first KPI we need to discuss now is how to compare and contrast the ways in which Mendeleev and Moseley organized the elements in the periodic table. According to Mendeleev's periodic table depended on arrangement the elements in ascending order of their atomic mass. Ascending order means by increasing the atomic mass. So the element that has a smaller mass, we put it first, and then the element that has a higher mass, and the one that has a higher mass, and so on. While Moseley periodic table was completely different because he organized the periodic table by increasing the atomic number. Then we need to describe the periodic table. The periodic table has an arrangement of elements in order of their atomic number so that the elements with similar properties fall in the same column or group. Looking back at the periodic table, you will notice the following. The periodic table has been organized in such a way the elements are arranged in increasing of their atomic number, as we have just said, but in a way that the elements that have similar properties fall in the same column or group. So here, for example, it's group 1. Group 1 contain elements that are all similar in their properties. Group 2 also contain a group of elements that have similar properties. Similarly, elements of group 18, elements of group 17, and the transition elements that lie in the middle of the periodic table, and the inner transition elements that are located below the periodic table. These are some grouping of elements. Each group have similar physical and chemical properties. Next, we need to distinguish between group and period in the periodic table. Each column, we call it a group. So group is a column in the periodic table. So how many columns do we have here? We can count the column. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So the elements in periodic table are arranged in 18 columns or 18 groups. Then, what are periods? Periods is a row in the periodic table. So each row constitutes a period. There's period 1, period 2, period 3, period 4, period 5, period 6, and period 7. Remember that those elements that are located at the bottom of the periodic table, they are part of periods 7 and 8. So you are not going to add more periods. This means that our periodic table, the modern periodic table, is made of 18 columns or groups and 7 periods. Again, to reconfirm, The periods are 7, 1, 2, 3, 4, 5, 6, and 7. The next point we need to discuss is the position of the main elements in the periodic table. Sometimes you are asked to sketch the periodic table to show the location of metals, nonmetals, and metalloids. Very simple. Metals are located on the left-hand side of the periodic table. All of those are metals, mainly group elements of group 1, group 2, and group 3 to 12. They are all metals except hydrogen. It is the only non-metal which locates in group 1. So all of those constitute metals. And then what are nonmetals? Nonmetals occupy the right-hand side of the periodic table, starting from period 4, group 4, or 14, 15, 16, 17, and 18. All of those elements are nonmetals. Of course, there are some exceptions, which include the third group of elements that we call them metalloids. Metalloids are occupying the middle of the periodic table between the metals and nonmetals. They separate the metals and nonmetals. So until here, we have metals. Starting from here, we have nonmetals, and those elements that are located in the middle, they are called metalloids, and they have a special color in the periodic table. And also you can distinguish the zigzag line which separate the metals from nonmetals. You can see this element, this is the group of elements that we call them metalloids. So remember, here we have metals, and on the right hand side we have nonmetals, and the metalloids are those in the middle of the periodic table, metalloids, that separate the metals from nonmetals. The most common metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. You can just remember 2 or 3 of them. Now we'll discuss some of the general properties of metals, nonmetals, and metalloids. Metals, generally metals, their physical properties including ductility, so they are ductile, shiny, good conductor of heat and electricity. While nonmetals are generally dull, brittle, poor conductors of heat and electricity. And metalloids, because they lie in the middle between the metals and the metals, so they have combined characteristics or intermediate characteristics between metals and nonmetals. So we can say that metalloids are conductors for electricity, but not as strong as metals. So they have electric conductivity, but the electric conductivity is an intermediate between the metals and nonmetals. And that's why the metalloids are used in transistors, in silicon chips, in mobile phones, and in some other equipments. Looking up the periodic table again, you need to distinguish the difference between representative metals or representative elements and transition elements. Representative elements include elements of group 1 and 2, and then groups from 13 to 18. From 13 to 18. These group of elements, we call them representative element. Representative elements. So again, representative elements include elements of groups 1 and 2 and group 13 until 18. While other elements, we call them transition elements. Transition elements are divided into two categories. The elements in the middle of the table, those elements, we call them main transition elements or metals, while the elements that locate at the bottom of the table, we call them inner transition metals or elements. So generally, elements in periodic table are divided into two categories, representative elements and transition elements. Representative elements, elements in group 1, 2, and 13 to 18. And they possess wide range of chemical and physical properties. Transition elements, elements in groups 3 to 12, and they are the typical metals that you know. They include iron, they include cobalt and nickel and zinc. They are shiny metals and they are very good conductors for heat and electricity. While the inner transition elements, they have also specific physical and chemical properties. We'll discuss them later. Now we are discussing the families in the periodic table. We need to list different families in the periodic table and identify the number of the group and elements present. First, the first family we have is the family of alkali metals. Alkali metals are elements of group 1 except hydrogen. Alkali metals. Second family, alkaline earth metals, and these are elements of group 2. Alkaline earth metals. Halogens are elements of 17th group. Halogens. And noble gases are elements of the 18th group. Noble gas. And now we are going to list general properties and some uses of some categories and families in the periodic table, starting with alkali metals. Alkali metals, looking at their properties, they are extremely reactive, mean they are very reactive. They react very vigorously with water and air. They have silvery appearance. They are soft enough to be cut by knife. The most important element of those is sodium, because sodium is one of the components of the table salt. So it's used in making table salt, which is sodium chloride. Lithium, all of you are familiar with lithium because it's used in lithium batteries that we are using in our mobile phones. Let's go to the second family, which include alkaline earth metals. Alkaline earth metals, they have also some specific properties, general physical ones. They are hard, or at least they are harder than alkali metals. They are denser or have higher density. They are stronger. They have higher melting point and boiling point than alkali metals. But they are less reactive. Of course, when you are talking about reactivity, we are discussing here chemical properties, not physical. They are less reactive than alkali metals. Regarding uses of some common elements in group 2, magnesium is a light element, and that's why it's used in fabrication of laptops and other electronic devices. Calcium, all of you studied calcium in biology. It's a very important mineral for health. Of your bones and skeleton. And also for the health of your tooth. Going to the far right side, we have two important groups of elements, nonmetals, group 17, which include halogens, and group 18, which include noble gas. Halogens, as you know, they occupy the far right side of the periodic table. They are very reactive nonmetals, or the most reactive nonmetals. We said when we are talking about reactivity, we are explaining the chemical properties. They react with most metals and form salt. Most metals and form salts. We have some uses, we can discuss them here. First is fluorine. I think that many of you are familiar with fluorine, which is added to the toothpaste and to drinking water to prevent tooth decay, and also chlorine Yes, you are also familiar with chlorine because you know it's added for water for sterilization. So it's used in sterilization of water, drinking water, and also to the swimming pools. The last representative elements, groups of representative elements explaining now, is the group of noble gases. Noble gases, chemically, they are very unreactive, extremely unreactive. Their uses include lasers, light bulbs, and neon signs. Neon signs. Looking at the periodic table, you can predict that we can divide it into 4 blocks. So what are the blocks of the periodic table? You can distinguish here 4 blocks in the periodic table. The block on the far left side of the periodic table, we call this block S block, while the block of elements that lie on the far right side of the periodic table, we call them P block. Elements occupying the middle of the periodic table, we call them D block, and the elements that locate at the bottom of the periodic table, we call them F block. So the periodic table is divided into 4 blocks: S, P, D, and F. Sometimes you are asked to compare and contrast transition metals and inner transition metals. So let's draw a table. We'll compare the properties of transition metals and inner transition metals. Transition metals, by definition, they are elements occupying groups 3 to 12. Inner transition metals, they are located at the bottom of the periodic table. Normally, they are elements in periods 6 and 7. So they are located mainly in period 6 and 7, but we are moved them from their position in period 6 and 7 to the bottom of the periodic table. Those elements, we call them main transition metals, while the inner transition elements, we divide them into 2 groups: lanthanides that occupy period 6 and actinides that are located in period 7. You might be asked also to describe some properties and uses of lanthanides and actinides. So we are going to draw another table to compare lanthanides and actinides. Remember the question of compare and contrast. You should mention one similarity at least and list some differences. So I will write here lanthanides and on the other column actinides. Lanthanides, first, let's write the definition. Lanthanides, they are with a group of elements with atomic number. They have atomic numbers from 57 to 71. They are 15 elements. They are all metals, including scandium and yttrium. They are not located in the same position of other lanthanides, but they share their properties. Also, lanthanides, what we call them? We call them rare earths. They are rare metals found on Earth's crust. Their physical properties include they are shiny or silvery, white metals, and you can find them in some ores. Ore is the natural composition of the element in the Earth's crust. Normally, elements, when they exist in Earth's crust, they are found in the form of complex compounds. Some of those compounds, within those compounds, we can see lanthanides. Whereas actinides, also they are 15 elements in the periodic table. They have atomic number range between 89 and 103. So remember the difference between lanthanides and actinides. They are named after the first element in the series. The first element in the series is actinium, so they are called actinides. In the same way, lanthanides are called after the first element in the series, which we call it lanthanum. So we call the whole group lanthanides. Most of them are man-made metals. Except uranium and thorium. Man-made. So they are not naturally occurring elements. Uranium and polonium or plutonium are used in nuclear reactors and the nuclear bomb. Actinide, americium, is used in a smoke detector. Very brief, the uses of lanthanides include hybrid cars, superconductors, and permanent magnet, while the uses of actinide involve uranium and plutonium are used in nuclear reactors and nuclear bombs, while americium is used in smoke detectors in airplanes. Now we need to learn more about what we call valence electrons. What are valence electrons? Valence electrons are electrons in the outermost energy level of an atom. Electrons in the outermost energy level of an atom. We need to identify the number of valence electrons in different groups in the periodic table. Group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Group 3 elements, or 13, they have 3 valence electrons. Group 14 or 4 have 4 valence electrons. Group 15 or 5 has 5 valence electrons. Group 16 or 6, they have 6 valence electrons. Group 17 or 7 have 7 valence electrons. Group 18 are noble gases, or group 0 or group 8 have 8 valence electrons. So the number of valence electrons agree with the group number in the periodic table. Don't get confused between the valence electron and valency. Valency is the number of electrons that the atom needs to gain, share, or lose to be octet or to reach the structure of the nearest noble gas. So if you have an element in group 7 and has 7 valence electrons, in order to be stable and reach the structure of the next noble gas, it needs to gain 1 electron. So the valence of this element is 1. Similarly, sodium, which lies in group 1 in the periodic table and has 1 valence electron, in order to reach the structure of the noble gas, the closest noble gas to is, what is the closest noble gas to sodium? The closest noble gas to sodium is neon, which is just 1 point behind it. So sodium will lose 1 electron to be octet or to reach the structure of the noble gas. So here we can say that also sodium has a valency of 1.